Hi everyone, today we're going to talk about enthalpy of reaction. This is tied to learning objective from the College Board that the student can interpret observations regarding energy changes and to generate relevant symbolic and graphical representation. And the student able to use calculation to relate energy changes associated with a chemical reaction to the enthalpy of the reaction. Enthalpy change, which is represented by delta H AHxn of the reaction. It is the amount of heat absorbed or evolved in the reaction under constant pressure. It is described on a per mole or per gram basis in kilojoule per mole or kilojoule per gram. It is a state function that represents change in the heat content, so it's between final and initial states. Therefore, the enthalpy change of a reaction is equal to the summation of the enthalpy of all the products minus the summation of enthalpy of all the reactants. In an exothermic reaction, the energy of the system decreases. Energy is lost by the reacting molecules in the system, but gained by the surrounding. As thermal energy flows from the system into the surrounding, temperature of the surroundings will increase. Heat is evolved, surroundings feel warm. Example will be combustion of methane, that heat is released, and this enthalpy change is negative because it's equal to product minus reactant, and product has lower energy than the reactants. In an endothermic reaction, the energy of the system increases. The energy is lost from the surrounding but gained by the system. So when thermal energy flows from the surrounding into the system, temperature of the surrounding will decrease. Heat is absorbed, surrounding feels cool. Example would be melting of ice. Gaining heat to melt ice solid into water liquid. The enthalpy change is positive. Now here we have diagrams of exothermic versus endothermic. On the left-hand side, we have exothermic reaction. So we start up with higher enthalpy of the reactants going to a lower enthalpy of the products. Heat is released by the system to the surroundings in a negative sign. On the right-hand side with the endothermic diagram, we have a lower enthalpy of reactant going up to high enthalpy of the product. So the enthalpy has to be gained from the surrounding as positive. Practice problem number 1. Classify the following as endothermic or exothermic. Indicate the sign of delta H. Water boils to form steam. Now we have to add heat to it, so this is endothermic. Delta H is positive. When water freezes to form ice, the liquid to form solid will be releasing heat to the surrounding. This is exothermic. Delta H is negative. When the ice popsicle melts, again, it's gaining heat to melt it into liquid. This is endothermic. Another example, if a child is having fever and the mother would wipe his body and forehead with an alcohol towel so that he would feel better afterwards, reducing the body temperature. This is absorbing heat from the body to vaporize the liquid ethanol into gaseous ethanol. And this is endothermic reaction. Delta H is positive. Now, when ammonium nitrate crystal dissolves in water, temperature of the solution decreases. Ammonium nitrate is absorbing heat from the water. This is an endothermic reaction. Delta H is positive. When we add concentrated sulfuric acid to water, the solution gets very hot. Going from liquid state into aqueous state, heat is released. This is exothermic. Delta H is negative. Try practice problem number 2. Determine the enthalpy change from the diagrams. Now in here we have, starting with the reactant at 10 kilojoule per mole and the product ending with 2 kilojoule per mole. The enthalpy change is the product enthalpy minus reactant enthalpy. Therefore we have negative 8 kilojoule per mole. And with the negative sign, we know this is exothermic reaction. Now with the other diagram, we start up with 10 kilojoule ending up with 14 kilojoule. So the product is at 14 minus 10 kilojoule of the reactant enthalpy. We have positive 4 kilojoule per mole. This is endothermic reaction. In writing a thermochemical equation, we want to make sure that other than writing the balanced equation, we have consideration for the enthalpy term. Now we either write it as heat energy 2044 kilojoule on the product side for an exothermic reaction, or we would take it out of the reaction and write the enthalpy change as negative 2044 kilojoule. The magnitude of the enthalpy change of a reaction is related to the stoichiometric mole ratio. So this 2044 kilojoule of heat is the heat released per 1 mole of propane reacting with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water. In an endothermic reaction, we write the enthalpy as a reactant on the side of reactant, or we can take it out of the equation and state it as positive value, knowing that this is endothermic reaction. It means 90.7 kilojoule of heat is absorbed when 1 mole of mercury 2 oxide is decomposed to form 1 mole of mercury liquid and half mole of oxygen gas. Practice problem number 3. In a thermite reaction, the reaction between aluminum and iron oxide to form aluminum oxide and iron. The enthalpy change of the reaction is negative 823 kilojoule. How much heat will be evolved if 50 grams of aluminum reacting with 175 grams of iron oxide? Now, obviously, this is a limiting reactant problem, and we have to calculate the heat generated by both reactants and compare them to decide which is the smaller amount of heat released. Taking the 50 grams of aluminum converted into moles of aluminum and multiplied by negative 823 kilojoule tied to 2 moles of aluminum from the equation, we have negative 763 kilojoule of heat. Taking 175 grams of iron oxide converted into moles of iron oxide and then related to 1 mole of iron oxide for negative 823 kilojoule of heat released, we calculated to be negative 902 kilojoule. Now, obviously, the aluminum produces less heat. Therefore, it is a limiting reactant. The heat release is 763 kilojoule. In practice problem number 4, consider the particulate drawing, the combustion releasing heat of negative 1530 kilojoule. Now let's take a look at the particulate drawing. We start out with 2 moles of methanol, CH3OH, and 3 moles of oxygen to form 2 moles of carbon dioxide and 4 moles of water. So we need to write a balanced chemical equation. We need to calculate kilojoule of heat released when 100 milliliter of the liquid methanol with a density given are burnt in oxygen. And finally, what's the volume of oxygen gas to combust in order to release the amount of heat in B at room temperature and 1 atmospheric pressure. So here is the balanced equation with the enthalpy being listed as negative 1530 kilojoule in an exothermic reaction. Take 100 milliliter of methanol times density to convert it into 79.1 gram of methanol and then convert it into 2.47 moles. And then tied it to the heat energy term of minus 1530 kilojoule per 2 moles of methanol, the coefficient that we get from the balanced equation. This is equal to negative 1,890 kilojoule of heat released. Then we take the moles of methanol and using dimensional analysis and stoichiometric mole ratio to convert into moles of oxygen. 3 moles of oxygen are combined with 2 moles of methanol from the balanced equation, producing 3.71 moles of oxygen. Now then we use the ideal gas law to find volume, nRT over P, and we then have 90.8 liters of oxygen formed. To summarize what we have learned today, we learned the energy differences and macroscopic observations between exothermic and endothermic reactions. We learned to use graphical representation of enthalpy changes in reaction to find its value of delta H. We classify whether the reaction or the process is exothermic or endothermic in various situations. We interpretate the thermochemical equations, and finally, we use the calculation to relate enthalpy change to energy change associated with the reaction. We hope that you have found this video helpful. If you like it, please give us a like, and we look forward to seeing you in the next part of the video.